Rational functions are a natural continuation to studying polynomials. Polynomials are powers of, say, x, for instance, x squared, x cubed, or a combination of these, like x to the fifth minus x cubed plus x squared minus 17. These are all polynomials. A rational function now has a division in it. So it's like f of x is a of x over b of x. These could be other sorts of functions, but for now I am just going to stick with rational functions. The most common first rational function that you may encounter would be 1 over x. Now, from last video, we can plug in negative x for the x, and this gives us negative 1 over x, which is negative f of x, which would be an odd function. And if we were to graph this, we could make a little table. We cannot use the point 0, but we can use 1, and 1 over 1 is just 1. If we go to 2, it's now 1/2. If we go the other way, 1/2, well, now it's 2. Now it's 2. Plotting this will look something like that. And because of even-odd symmetry, it'll be symmetric to the origin. It will never actually reach the y-axis or the x-axis in either direction. These are known as like asymptotes, which can be found. I'll go over them in a little bit. Another maybe common rational function could be 1 over x squared, and because now it's a even power of x, it's now a even function. And graphing this just is the same thing, except now it's symmetric on the y-axis instead of the origin. Sometimes a rational function is actually much simpler. For example, if we divide two polynomials, like a quadratic divided by a linear equation, for simplicity, I will be writing the quadratic like this, and then the linear equation like this. We can cancel out these two terms, and we're just left with x minus 2, which would be a straight line. And then when x is equal to negative 2, it looks something like that. When x is equal to negative 2, though, there's this hole there which indicates a discontinuity. It can never equal that value. Let's consider another function. Let's consider the function f of x is equal to 2x over x squared minus 1. To find the vertical asymptote, we set the denominator equal to 0. X squared minus 1 is equal to 0. And through some basic algebraic steps, we can say that x squared is equal to 1, or x is equal to plus or minus 1. A horizontal asymptote is found by comparing the degree of the numerator to the degree of the denominator. The degree of the numerator is 1, the degree of the denominator is 2. When this happens, the horizontal asymptote is the line y is equal to 0, or the x-axis. If this were flipped, if it were like x squared minus 1 over 2x, now the numerator is greater than the denominator. The horizontal asymptote may not be there. It actually isn't there for that instance, and it will have a slant or oblique asymptote, which is like a line that it would follow that it could never pass through that specific line. This specific line is found using polynomial long division and other steps. For this g of x function, that line is just y is equal to 1/2 x. I won't go over that step. I don't really find it that necessary. You don't really use polynomial long division so much later on. But if anyone is curious, I can cover it. Okay, let's graph this. Graphing this is not so hard. We're going to look at the 3 different regions: when x is greater than 1, when x is less than 1, negative 1, and when x is in between 1 and negative 1. The 3 different regions. Again, greater than 1, less than negative 1, in between the 2. Now, when we look at the behavior of, say, when it's greater than 1, because the degree of the denominator is greater than the numerator, it will go towards infinity much faster. It grows a lot faster. So for very high values of x, it's going to mirror 1 over x. So when we go and draw this for outside the asymptotes, it's going to be a lot like 1 over x, where it follows this, and because we already said it's an odd function, it's going to be exactly like that too. Now the mystery then is just finding out what happens in between, the in-between region. So we are going to find out when it crosses the x-axis, and that's when the numerator is equal to 0, and that only happens when 2x is equal to 0, and that only happens when x is equal to 0, so we have that point 0, 0. And then we're going to kind of just make a guess a little bit on how to graph it after that. For values in between negative 1 and 0, the x squared minus 1 term is going to stay negative. The 2x term is also going to be negative. So when you have two negatives dividing each other or multiplying each other, you get a positive. So it will go towards that direction. And the same argument for when we get positive values in between 0 and 1. X squared minus 1 is going to be negative, and 2x is going to be positive. So this will be going in that direction. And that's just the general idea on how you plot this one. But as I said, I'm not going to go over any more examples just because I feel like this was more than enough. Anyway, thanks for watching.